by Chen from UC Irvine, and it's about ZigZag supporting similarity queries on vector space model.
All right, I'm Chen from UC Irvine. This is a journal work with my collaborators from Wuhan University in China. So let's consider a case where we have a table with records about employees. Every employee has certain skills. For instance, Alice has R scale, writing, stats, and programming all have other skills. So in addition, for every record and also every skill, we have an indicator about how good a person has a skill. Like Alice has average R scale, and she's very good at stats. Similar argument is true for Bob. So given such a table, let's assume we have a human resource manager who is looking for employees that meet certain skill requirements. Here, let's say R, stats, and database. And our goal is, from this collection of records, we want to find those employees who participate. Right. So we want to, from this table of records, to find all those records that meet these conditions. So due to the nature of the problem, it is very reasonable to assume not every record meets all the conditions. In fact, since everybody has different kind of skills with different levels of efficiency, we want to find those records that match those conditions. So one natural question is the context is, in general, how do we quantify the similarity between two records? In our work, we consider a few factors in our similarity function. The first one is we assume every scale has a global weight. So here, like art has one scale weight of number 1, programming has a weight number 4. In addition, we also assume every scale and also every employee record, they have a very record-specific weight. Now, to be less confusing about these two notions of weights, we'll name the second one as a degree. Now, these ones is similar to the traditional setting in document search where we use TF-IDF. So you can say this is a TF-IDF setting is a special case of this setting, but our work is considering a more general setting where the TF, so-called TF, might not necessarily be the token frequency, and also the IDF can be arbitrary. The question becomes, given these factors, how can we do the search very efficiently? So formally speaking, the problem we are looking at is we have large collection of records, and this is the ranking function. And the ranking function at a high level we consider TF and IDF. And we want to have a threshold, and all the matches should meet this basic threshold requirement. Of course, we have to do it very efficiently. Now, one question is how good this function is. We did an experiment to evaluate different functions, including like a Jacquard, cosine. And since one side of it is different functions, they have different semantics. So what we did is for every function, we picked a threshold, and we did a search, and we knew the ground truth, so we can know the precision recall. So we plot this figure with all different lines. And the main idea is if we fix one particular recall, we look at the positions of different functions, and the one with the highest position, we assume that's a good one. So in this simple experiment, the main message we want to give here is the function we're choosing can indeed give us very high quality. I want to make it clear, the focus of our work is not to propose this function. Instead, our focus is if the application requires this kind of functions, how can we do this kind of search very efficiently? So this is a high level of our contributions. And at a high level, we come up with some index structures by extending the classic inverted index, by doing some very clever organization. And we come up with a family of algorithms that can use this index structure very efficiently. Due to the time limit, I'm going to just give you an overview of one or two of the algorithms in the paper. So naive algorithm is very simple. We go through the tokens in the query, and for every token, we have an inverted list. So we go through all the lists, and for every list, for every record, we have this function, and as long as this function is satisfied, this is a candidate. This is a very naive method. So what you could do is, as we go through the list one by one, I want to look at a particular list, even though at that moment for that record, we don't know the kind of some information about the remaining weights. We can still calculate the upper bound of those remaining values. We can use the upper bound of the remaining values to do some pruning. So if this guy does not satisfy this inequality, we can prune it. So we don't need to scan all the lists. So the next idea is even more clever, which is very specifically to our ranking function. We can show that for every list, we do not need to look at all the records. In fact, we can derive a range of all the possible lengths, and we can just order all the records within one list based on this length. And we only look at a subset of those records. We can do further pruning. What's even better is we can show as we go through the list one by one, as we collect more information about those records that have been pruned, have been deleted, we can further tighten the range bound as we go through list. In other words, as we go through, we see more lists, as we see more records, we can derive tighter bounds on all lists. So this tighter bound can even help us do more pruning. So other results are in the paper, like we have some other techniques to shrink the length of each record, and we can also use this idea to iteratively make the bound even tighter. So we did a whole bunch of experiments using 3 real data sets, and each data set has at least 30 million records. And we also consider different memory settings, like in-memory, on-disk, flash drive. So this is one of the figures to show the performance numbers of all the algorithms we have proposed. Right, so this is my time. So if you have any questions, please feel free to ask.
Then I have a question. Sure. And without understanding a lot of the details, so I see that you have a comparison with the cosine similarity. So you have 2 vectors, and then you have the comparison which basically is saying how similar these are, right? So if I just ignore the legs, is it going to become what you have exactly equal to cosine similarity?
Correct. A cosine is a special case of our function. So this is more general. So in one of the first figures I showed, cosine was one of the functions we compared with, and this function is indeed provided a higher quality.
Yeah, and in the comparison, you have the legs, and therefore cosine is not fulfilling the function, right?
Correct, correct. We give the application more flexibility to quantify the importance of every token.